Today, I'm going to be talking to you about secret key recovery in a global scale end-to-end encryption system. And this is joint work with the lovely people at Signal Messenger, Graeme and Rolfe, and also with Emma and Raluca at UC Berkeley. So first, I'll begin by telling you a story about Bob here. So Bob is using end-to-end encrypted messaging, so an application like Signal. Bob is really happy because Bob gets all of these great privacy and confidentiality guarantees from end-to-end encrypted messaging. But life happens, and Bob maybe breaks his phone. Along with his phone goes his secret key, and now Bob is displeased because he can't decrypt or recover his user account because everything's encrypted and there's no decryption key. So actually, a couple of months ago, I was Bob in this case, in that I went skiing. I took a fall, and then my phone just disappeared into the snow. It fell out of my pocket. It's still on Lake Tahoe somewhere. And so 2.5 months ago, I was like, oh, did I just use SVR to recover my keys? So anyways, let's talk about how we actually back up our secret keys. So one thing you could do is just hand over your secret key to Signal and say, like, hey, store this for me in case I ever need it. Unfortunately, this means you are giving your secret key over to Signal, and Signal can now read your encrypted messages, and you kind of undermine all of the reasons you are using end-to-end encrypted messaging. And you could also print out paper keys. This is a way of storing your secret keys, but it's not user-friendly. It's kind of hard to expect your average user to be able to store a high entropy secret for a long period of time. And instead, what you could do is use a low entropy pin to derive the secret key. And actually in Signal's Messenger UI, you always get reminded to re-enter your PIN, because without it, you can't recover your secret key. Unfortunately, because the PIN is low entropy, that means it can be brute forced. And at Signal and other end-to-end encrypted secret key backup services, usually you mitigate this by limiting the amount of PIN guesses you can make to a certain user's account using secure hardware. Now, with secure hardware, they're kind of known for compromises to happen. There's attacks on them all the time. So if you have a single type of secure hardware, that means it can be compromised. So for SVR3, or in our system, what we do is we use this low entropy pin to, instead of deriving just one secret key, we derive shares of the secret key, and each share has an enforced guess limit, and we split these shares amongst what we call trust domains. The motivation here is that heterogeneous secure hardware is unlikely to be compromised all at once, and no single trust domain here can compromise Bob's secret key, because if you compromise one trust domain, you just get a share of the key. You have to compromise every trust domain to be able to reconstruct the entire key. And actually, I have shares asterisk here because these are actually masked shares. The paper has more details about the cryptography in the system, but you can think of the architecture we have here as being a little bit cryptographically agnostic, in that we could swap out how we secret share the key as long as we have this assumption of splitting it across trust domains. So this system is called Secure Value Recovery 3, or SVR3 for short. And to our knowledge, it's the first cross-enclave, cross-cloud deployed system for key recovery. And that means inside these trust domains, they act as logical servers, but inside we're actually running a cluster of servers on different clouds on different type of secure hardware. It defends against internal and external attackers, which I'll define in the next couple of slides. And there's a capacity for 500 million users at about 0.1 cents per user per year. And the roadmap of this talk is, first I'll talk about the layered security guarantees of our system. Then I'll talk about how we actually build an SVR3 backend. And then I'll give you a brief evaluation summary. So first, the layered security guarantees require me to define what actually a trust domain is. And a trust domain is comprised of a replicated enclave cluster running on a single type of secure hardware on a single cloud provider. So like I said before, it all acts as one logical server, but behind the scenes, you have a replicated enclave cluster running inside each trust domain. And that means when you have different trust domains, you have heterogeneous secure hardware and clouds. So in our deployment, we have Intel SGX on Azure, we have Nitro on AWS, and then AMD SEV-SMP on Google Cloud. Now, in order to tell you about the security guarantees, we have to talk about the attackers that we're interested in defending against. And this is a little new in the sense that we have a couple types of attackers. The first one is actually Signal itself, so the organization or the system administrators or the people that are providing the service. And that means that they can, compromise the deployment. They could spin up and spin down machines. You could deploy malicious code on the servers, and you don't have any physical access to the cloud machine since it's running on the cloud, but you can think of it as having like root access. The second type of attacker we want to defend against is the cloud provider itself. So for example, Microsoft Azure or Google Cloud. The cloud provider has physical access to the deployment. And that means they could mount things like DIM interposer attacks, where you're interposing between the system bus and the memory module. And that means you could do this idea of, you could mount physical rollback attacks, which I will talk about in more detail in a later slide. The third type of attacker, which I'll gloss over, is you can just think of it as your external attacker who's a hacker, and they could become a type 1 or type 2 attacker by compromising the cloud or phishing like a Signal employee. So the security guarantees that our system provides are when we deploy on n trust domains with m replicas per trust domain, and we have these parameters T and S, our system can, without letting an attacker compromise the user's secret keys, tolerate total compromise of at most T trust domains. So this is what we consider security across the trust domains, and that a trust domain can go down and the user's secret keys will still be safe. But also, we've tried to make it harder to compromise a trust domain through rollback attacks. So we can tolerate rollback attacks that are done through software, and we can tolerate at most S physical rollback attacks inside each trust domain before that trust domain is considered totally compromised. So in our deployment, to give you some concrete values for these numbers, we're running 3 trust domains. We have 7 replicas inside each trust domain, and we can tolerate 2 of these trust domains being totally compromised before user keys are compromised. And we can tolerate inside each trust domain at most 2 physical rollback attacks. So you have to roll back 2 of the enclaves inside the trust domain simultaneously. With respect to availability, we provide availability when T+1 trust domains are operating correctly. And what that means is that the enclaves in the trust domain are online, and that none of the enclaves in the trust domain are under attack. This is analogous to what we call normal, what you can think of as normal operation. And this is because if we're under attack, we want to prioritize safety over availability because user secrets are very sensitive. But also note that in the types of attackers I've defined, Signal is one of them. You could easily deny service if you're Signal by just unplugging your deployment, just taking it down. So now let me talk about how we build an SVR3 backend. And first, because we're running different types of enclaves, this sort of requires us to have a definition of what an enclave is providing us with respect to security. So first, we require 3 things. The first one is application level attestation. And what this basically means is that the enclave can prove to you that it's running certain code before you interact with it. The second one is memory access control, and that if you're not inside the enclave, you cannot access the enclave's memory. So usually this is done through hardware enforced access or encryption to prevent cold boot attacks. And the third one is that we assume that the attacker has page-level rollback granularity. So it can roll back memory at the granularity level of pages, but not anything more granular. And just note that even if an enclave type loses these guarantees, then the trust domain of that enclave type is considered compromised. But like I said in the security guarantees before, our system is still protecting user secrets when at most T of these trust domains are compromised. So you can tolerate losing these enclave guarantees in some trust domains. So let me now talk more about rollback attacks. Enclaves are notoriously susceptible to software and physical rollback attacks. And you can think of the software rollback attack as something that can be mounted by a type 1 attacker. Physical rollback attack can be mounted by a type 2 attacker. So rollback attacks they kind of undermine the purpose of the system because the system is supposed to limit how many guesses you can make on a user key. And that means, if you're an attacker and then the guess count for a user is 2, you make a guess, it's 3, you roll it back, the guess count is 2, you can make another free guess, and you can do this, forever. Software rollback attacks are done through external state that are stored by data sealing. So data sealing is this enclave mechanism in which you can persist state in the enclave outside of the enclave. And you can easily roll this back by restarting the enclave and feeding it old state that it persisted. We protect against this by just storing the entire database in memory. So if you never store external state, there's no external state to roll back. The problem here is that now your database is inside memory, and that's volatile. So if your machine falls over, you lose your database, and that's not great if you're trying to provide a service. So what we do is inside each trust domain, we are replicating and running a cluster of enclaves using Raft. And that gives you, some fault tolerance. Yeah. So hardware rollback attacks, on the other hand, are when you are rolling back internal memory during execution by interposing on the system bus. And vanilla Raft is a crash fault tolerance protocol, which means it loses safety guarantees in the face of hardware rollback attacks. The observation we make here is that it's definitely harder to mount a physical rollback attack, but we can get extra security if we make it harder to compromise the trust domain by requiring you to roll back to mount multiple physical rollback attacks at the same time. So we modify Raft and we introduce a rollback resistant Raft. And it's a rollback resistant consensus protocol with 3 changes. The first one is hash chain verification whenever we process new log entries. The second one is a supermajority so that the quorum intersection will include 1 non-rolled back server. And then the final change is a promise round before the leader proceeds with an update. The safety of Raft, which I'll informally state here, is that for every log entry that's been applied to the state machine of a server, if the number of physically rolled back servers is less than or equal to S, then that server is never going to apply a different log entry at that log entry's position. So it should not be equivocating on that log entry. For safety, we require, if you have M replicas in your cluster, to be more than S, but S can be smaller depending on how many crash failures you want to tolerate, and I'll go into that in the next slide. The paper has a TLA plus specification of our modified Raft protocol and also a full safety proof under the assumption of less than or equal to S physical rollback attacks. So for liveness, like I said with our availability goal, when the cluster is under a physical attack, you're more worried about safety than liveness. So when you're operating normally under no physical attacks, we require there to be the floor of the number of replicas you have in the cluster minus the number of hardware rollback attacks you want to tolerate divided by 2 crash failures to have liveness under normal connectivity conditions. And just to make this concrete again, that means 7 replicas, you can tolerate 2 physical rollback attacks, and then you can have 2 crash failures. And now I'll briefly just talk about the evaluation of the system. So the deployment details are that we have 3 enclave types in clouds. We have Azure using Intel Scalable SGX, Google Cloud using AMD SEV SMP, and AWS Nitro. And we provision for 1 request per second per million users and about 256 bytes of memory per user. This 1 request per second per million users is because although key recovery is an important operation, it doesn't happen that frequently in the sense that I'm not losing my phone every day. The deployment supports a capacity of 500 million users at $0.0009 per user per year. And the evaluation numbers are on a staging cluster that's provisioned for 10 million users. And these are the machine types that we use on each cloud. So on AWS, we use M5.X large instances. On Azure, it's DC2S v3. And then on Google Cloud, it's N2D standard 2. So the end-to-end performance, we have an average end-to-end latency for recovery and storing key operations to be 365 milliseconds. The average throughput is around 1,000 requests per second. And to just give you an idea of where the time is going for this end-to-end request latency, we see about 30% of the time going to attestation. A super small amount of time actually goes to the cryptography. I'd say the rest of the time goes to waiting for the servers to return. So in that call to the server is running consensus, getting the log entry applied to the distributed log, and then checking the guest count. If the guest count is higher than the guest limit, it'll delete the secret, and then returning that to the client. And then the rest, 1% of the time, is actually spent on reconstructing your key after you get your shares back from the servers. So in conclusion, SVR3 enables secret key recovery in a real-world setting by distributing trust across heterogeneous secure hardware. And yeah, thanks. I'm happy to take questions. Here's a link to the paper and the code repo. And yeah, thanks for your time.